Okay, so I'll just go a little bit deeper into the parallel architectures and programming models, just give you a very bird's eye view of that to understand that what we are going to focus on in this course. So if we talk about parallel architectures, right, there are primarily two architectures, shared memory and distributed memory, and then there's a third architecture which combines them both, which we call hybrid. So let's quickly have a look at what that is. So in shared memory architectures, what happens is that you have a memory unit, right, and this is accessible to multiple CPUs. So there's CPU 1, CPU 2, CPU 3 and so on. Right, so there's a single memory unit that is shared by all the processors. Okay, that's why it's called shared memory. So typically there's a common bus that sits between the memory and the processing units, and all the CPUs share that bus, so they have to, you require an arbiter to figure out which CPU gets access to the memory, right? So anyways, we'll get into more details of this later, but just to understand that that is what shared memory means at a high level. So what happens in distributed memory? So in distributed memory, what happens is that every CPU has its own memory unit. Okay, and now what these, but obviously if you're trying to solve a large problem and you're trying to do it in parallel, you need to divide the problem and you need to sync up at various points. So these processors need to talk to each other, right? So how do they talk to each other? So typically what happens is that there is a network. So there are lots of different types of networks. Again, we'll get into that later. But for now, it's just important to understand that there is a network that connects all the processors, right? And each one of them has its own memory. So now, what is the issue with shared memory? The basic issue with shared memory is that it's not very scalable, right? Because how many processors can you add? Because they're going to use the same bus to access the memory, right? So there's a limit to the number of CPUs that you can add. So typically in modern day processors, you see 8 cores, 16 cores, right? Some research processors are pushing it to about hundreds of cores. But that's, there's a limit to it. That's where it will end, right? You can't go beyond that. But in distributed memory, because each CPU has its own memory, right? So you can just replicate this and you can have as many processors as you want. So the bottleneck is going to shift to the network. So it all depends on what kind of a network you design, right? So there are different kinds of networks, completely connected network connecting all the processors together, or you may have some simple network like similar to Ethernet or something which is shared across all the processors, right? But the important point here is that the bus is not a bottleneck, right? The bottleneck shifts to the network, and depending on how you design the network, you can scale this to a large number of processors. And finally, what we use in real life, what we see in real life is neither the shared memory or the distributed memory system, but a hybrid of the two, right? So typically what happens is that you have different nodes which are connected together by a network, and each node has multiple CPUs sitting on it. CPU 2A, CPU 2B and so on. Right, and similarly you have multiple CPUs sitting over here, right? So locally on each node, it's a shared memory architecture, right? If you look at one of these nodes, it's a shared memory architecture, but if you look at across nodes, these two nodes are connected together using a network, so that's the distributed memory part of it, right? So this is called a hybrid system, okay? So just as you have parallel architectures, there are different programming models to write code for these, right? So there's the shared memory model, and what the shared memory model assumes is that there is one huge global address space. So think of it as the memory, right? So you assume that there is one global memory that is visible to all the processors or all the tasks. So all the tasks get to see the same global address space, which means that if one of the tasks writes something to the global address space, that is visible to everybody else. Okay? And the other is the message passing. In message passing, what happens is that each task gets to see its own address space. Right? So it's private. It's only visible to this task. So each task will get to see its own private address space. And now, if one task wants to, get some data which resides with another task, how does it get that data? So you have to explicitly do message passing. That's why it's called the message passing model. You have to explicitly send data. So the programmer has to write code to send the data across to another task, and the other task has to write code to receive that data, right? So this task will have to receive that data. Okay? As you can see, right, in shared memory, there's no send receive involved because everybody gets to see the same data. All you need to do is write into the memory. It's visible to everybody else. They can just read it off from the memory, right? And in case of message passing, you have to do explicit send receive communication. So as you can see, right, if you look at the left hand side and the right hand side, it's quite obvious that the shared memory programming model is kind of like suited to the shared memory architecture, and the message passing model is suited for the distributed memory architecture, right? Because the send receives happen over the network, and here, because all of them have access to local memory, all of them can use that as the global address space. Okay? But that's not necessarily true. So you can actually have a shared memory model which works on top of distributed memory. Okay? And you can have a message passing model which works on shared memory architecture. Okay? So what does that mean? So let's take this case, right? Message passing working on shared memory. A process has its own address space, even on the same node, on the same CPU, right? You can run multiple processes, each having its own address space. So they don't get to see each other's address space unless you do some explicit calls, right? And then you can actually encode message passing, you can encode send, receive, and so on using the shared memory. Right, so you can do that, and similarly when you do shared memory, you can do it across distributed memory where there is one global view of the entire memory, right? But here what happens is that when you access a variable which is lying somewhere else, it is the responsibility of the underlying operating system to somehow get that data for you. Okay, so to the programmer it's not visible that this is a distributed system. The only issue the programmer is going to have is that some data is going to come back to it very quickly, whereas other data will take very long to come back, right? Because underneath it there will have to be a communication over the network, and then data will have to be transferred over the network back to this computer. Okay? Right, but again, the most common way of using these architectures is that you use the shared memory model on shared memory architectures, and you use message passing on distributed memory architectures. Okay? What do you do on a hybrid system? So you use a combination of message passing and shared memory. Okay, so typically you have different processes running on different nodes of the distributed memory architecture, and within that you use a shared memory model to use the multiple cores that are there on the node. Okay. For shared memory there are lots of models, but one of the most common models is OpenMP, right? And for message passing, again, one of the most common models is MPI, right? So you have to write your code using MPI, which is a message passing interface, a library, and in OpenMP you have to adhere to certain directives, right, in order to program in parallel. And when you use a hybrid system, then you have to code up in both MPI plus OpenMP. You have to make use of both of them, right? Okay, so what are we going to do in this course? So this is intended to be an introductory course in shared memory parallel programming, right? So we will be focusing on the shared memory aspects. Okay, that is slightly simpler in the sense that you can start off with a sequential program, and you can incrementally convert it, introduce your OpenMP commands into that, directives into that, and make it run in parallel. And you don't require a huge infrastructure. You can do it on a node which has multiple cores. Even your laptops today have multi-cores, right? So you can, so it will be easy to work with that. On the other hand, MPI requires some redesigning of the code, right? It's not intuitive that data is not is distributed across different nodes, right? So you have to explicitly write send receive, you have to make calls to send receive and so on. So you have to redesign your code if you want to use MPI. So we'll focus on OpenMP, shared memory programming. So we will understand the concepts and programming principles involved in developing scalable parallel applications, right? We'll see how much we can scale. We'll try to scale up to 8 to 16 cores. And we'll use OpenMP and C to write the scalable programs for multi-core architectures. Okay, that's the plan. So this is going to be for both computer science and non-computer science students. I'm going to cover whatever basics of operating systems or architecture is required in this course. What is expected is that you have a reasonable understanding of C. You're reasonably comfortable with C. Okay. I'm not going to go into the basics of C programming, right?